Alright, hey guys, it's Mr. Anderson again. Welcome to Chapter 2 in Algebra 2. Today we are going to talk about relations and functions. And again, this is Chapter 2, Section 1 in the book. So let's get started here. First of all, our objectives for today. We want to analyze relations and functions, and number 2, use equations of relations and functions. Alright, first of all, what's a relation? A relation is not your cousin Millie or your Uncle Fred. A relation, remember, is just a set of ordered pairs. Okay. Remember, a set of ordered pairs is just the combination of x and y that go together on a graph. So that's a relation, a set of those. The domain are all of the x coordinates. Okay, so the domain are the x's in the relation, and range are the y coordinates. So again, maybe you can remember, x and y goes alphabetically, x then y, domain and range. D comes before R, domain and range. Maybe helpful. Keep this in mind, though, very, very important. When you're writing the domain and the range, you do not repeat values. So if the number comes up more than once in the domain, when you write down the numbers that are in the domain, you only write it one time. We just want to know what numbers are in the domain. We don't want to know how many times it comes up, okay? Alright, so here's an example. Here we're given this relation. Here's a relation. This is a set of ordered pairs. You notice we've got over here, we've got 2, 6. That's an x and a y. Okay, so that's a set of x and y. All of these are combinations of x and y. So altogether, this is a relation. Okay, so first of all, we want to find out what's the domain. Okay, well, remember what we're doing here is you were looking at all the x values. So these are all the values I'm going to look at for the domain. Well, what do we have? 2, 1, 2. Oh, came up again. I'm not going to write it again, though. And then 0, 1. Oh, we already wrote it, so we're not going to write that again. And then 3. So all we're going to write here is 0, 1, 2, and 3. It doesn't matter what order these are in. You could have said 2, 1, 0, 3 would have been totally fine. It doesn't have to be in that order. And then the range would be the y values, right? So here are our y values. Oh, notice, look at 4 and 4. We're not going to write that twice. There's a 0 and there's a 0. So again, we're not going to write that twice. But what we do have then is -6, 0, and 4 are the numbers that are in the range. Okay, so that's what we would do for domain and range. All right, just to review a little bit, relations can be written in several different ways. Ordered pairs, which we just looked at. They can be written as a table, a graph, or a mapping. So I just wanted to briefly go through those to remind you what those are like. First of all, a table. So here's an example of your ordered pairs, your relation, and then to the right here, all this over here is your table. So you notice over here 3 and 4 go together, and so notice 3 and 4 in the table. And then over here 7 and 2, and we have 7 and 2. So they just translate into the table. Mapping, remember what a mapping looks like. It's got the 2 ovals in it, and then on the left side over here, this is where you've got your domain, and this is where you've got your range. Remember, when we write the domain, we only write it one time. So notice, even though 2 came up twice here and here, we only wrote it one time in here. So 2, 1, 0, 3, and over here, -6, 4, and 0. What we do is we match up each x with each y. So here, 2 and -6 went together, so I drew a line from 2, to -6. And then I'll just, and then like for example, here's 2 and 4, so I do from 2 to 4. So you just draw the arrows to match up the x's and y's there. All right, functions. Now, function, the main thing to remember about a function is for each x value, there's only one y value that goes with it. Okay, so for each x there can only be one y. If there's more than one y in any way, it's not a function. All right, so let's take a look and see if this is a function or not. Okay, again, here's a set of ordered pairs, a bunch of x's and y's together. So can we figure out for each x that we've got, do we only have one y? Well, if you look closely at all these here, okay, so we've got 3, 4, 7, 2, 0, negative 1, negative 2, negative 2, 2, negative 5, 0, 3, 3. Well, if you look closely, these are the key ones here to look at. Notice we had 3, 4, and 3, 3. Well, if you look at that, that means when x is 3, like here and here, like here and here, then you've got two possible y's. Y could be 4 or y could be 3. So when x is 3, y could be 3 or 4. So that means this is not a function because the 3 comes up twice in the domain. Let's look at another example here. If you look closely at this one, let's look at this 4, 1, 5, 2, 8, 2, 9, 8. Notice 9, 8, 5, 4, they're all different. So that means in this situation, each x that we have, there is only one y that goes with it. So yes, this would be a function. We don't have any repeating in the domain. No x coordinates are repeated. All right, so within functions, there are a couple of different ways that can get split up. And so if you look at this little chart here, you notice, first of all, on the left side over here, it's the one-to-one function. Basically, that means that each x connects with only one unique y. Okay, so you notice 1 went to D, 2 to B, 3 to A. It only connected, they connected with unique ones. If I had another arrow drawn from 3 to B, it would, actually in this case it would not be a function because you've got two arrows coming from 3, so then that would make it not a function. But in this case, each x goes to one unique range, okay? But you notice that doesn't happen here on the second part here. You notice you've got 3 goes to C and 4 goes to C. That is not a unique y for those two. They both share the same y. So that is not considered a one-to-one function anymore, but it is considered an onto function because each y, the D, the B, and the C, they do connect with an x. And you notice the reason why this first one was not an onto is because C doesn't connect with anything over here. And then the last example here is it's both of them. So each x value connects with a y value, and each y value connects with an x value, so that would be considered both one-to-one and onto. All right, let's look at another example here. We want to state the domain and the range of this relation, and then determine whether it's a function, and then one-to-one, onto, both, or neither. All right, so first of all, you can see all the points there on the graph. Might help if we wrote them out as our ordered pair. So as an ordered pair, we've got 1, 2, 3, 3, 0, negative 2, 4, negative 4, negative 2, and negative 3, 1. Now, if you look at that, okay, let's look at the domain here first of all. What's the domain going to be? If we look at this, we have 1, 3, 0, negative 4, negative 3. Okay, we can write all of those because there's no overlapping. And then in the range, we've got 2, 3, negative 2. Oh, negative 2 came up again. I won't write it again. And 1. And so here's what you've got. You've got negative 4, negative 3, 0, 1, and 3 for your domain. The range is negative 2, 1, 2, and 3. So that's your domain and range. And then, is this a function? Well, if you look at each x that we have, when x is 1, there's 1 y. When x is 1, 2, 3, there's 1 y, 3. When x is 0, there's 1 y, negative 2. When x is negative 3, there's only 1 y, 1. And when x is negative 4, there's only 1 y, negative 2. So this is a function, and in a few minutes we're going to look at another way when you have a graph to more quickly tell if it's a function or not. But this is a function. And so then we want to look and see if it's a one-to-one or an onto function. what I would first do probably is look and see if it's a one-to-one is kind of what the pattern I would go in here. So you look at the x's and you notice here when x is 0 you have -2 for y, but also when x is -4 you have a -2 for y. So that means you have two x's that share the same y. That means it cannot be a one-to-one function because they have to be unique. They have to be different y's for each x. So it is a function, but it is not one-to-one, and so then that means it has to be an onto function. All right, discrete and continuous. Basically, discrete just means it's a graph that's made up of points. Okay, it's not a line. So it's just individual points. That graph that we just looked at a second ago, let me back up on purpose this time. That is a discrete graph, okay? It's a discrete relation. You notice it's just points. It's not a line. And then a continuous relation is something that's graphed, which is a line of some sort usually. And it's just going to keep going on and on forever. Usually equations are going to be continuous. We'll find that out in a second. Here's an example. This is the other way I was talking to you about where we can tell if something is a function or not. By the way, this is also an example of both of these graphs here. The curved parts are continuous. Okay, both of these are continuous because they're lines. So in this case, the first case here, you notice we've got this U shape. The vertical line test says that if you draw a vertical line anywhere on this graph, it will only cross the graph at one point for it to be a function. So you notice they drew a dotted line right here. It only crosses at one point right there. If I drew another dotted line over here, guess what? It would only cross at one point. If I drew one over here, it would only cross at one point. So no matter where I drew a vertical line, it always only crosses at one point. So this is a function. Now over here, it's kind of more of a C shape. And you notice the way they've drawn this dotted line here, it crosses in 1, 2 spots. This is not a function. Okay, so this is a way to tell a little more quickly if something is a function or not. And if you would have looked at that last example we had with the dots, you could have just drawn a dotted line through each one of those dots and seen that there was no more than one dot going through each line. Okay, so that would have been a quick way to do it. All right, so here's a situation where we're going to graph a relation. We're given an equation, y equals 3x minus 1. We want to find its domain and range, and then we want to figure out if it's a function and all the other stuff there. Okay. So first thing that you can do is just make a table of values to find ordered pairs, to graph this. Now there's lots and lots of x and y combinations that are going to work here. We're just going to pick a couple and then draw a line through those. So here's an example of what you could do. You could pick -1 for x, 0, 1, and 2. That gives you 4 points. All that we need to do here is, once you know, if you pick -1 and you put -1 into this equation up here, that means you've got y equals 3 times -1 minus 1. If you work that out, what do you have? -3 minus 1, which is -4. There's your y. Okay, you notice there's where we got our y. You just do that every single time. Plug in 0, and you go 0 times 3. 0 minus 1 is -1. So you get some points there, and then you can graph those. You could also plug these into your calculator, your graphing calculator. I'll probably go over that more with you in class, but basically there's a y equals button on the upper left hand corner, and you can go up there and type in the equation and then hit graph, and then when you hit second function and then graph again, that actually gives you the table of values. We'll go over that more in class, but there is another way to do this as well. So we're going to graph these next. There are ordered pairs, and here's what they're going to look like on a graph. Notice we drew a line through all of those. Because it's an equation, there's a lot of x's and y's, not just the ones that we picked, so there will be a line that will go through all of those. Okay, so let's figure out what we need to here. Domain and range. All right, so I've got D here for domain. Remember, what's domain? The x values. Okay, well, wherever this graph is, okay, that's where our x values are. So this line is going to keep going and keep going and keep going this way, and it's going to keep going and keep going that way. So where are the x's that get used on this graph? Well, if I pick this point of 1 for x here, does it get used? Well, yeah, 1, 2. There's a spot there. What if I go to 2 on x? That gets used. It's up here. If I pick something in between, 1.5, is it? Yeah, there's a point. So every x that you pick, if you keep going out here to the right forever and ever to the positive infinity, you will keep finding points. They may be very, very big points, but there will be points that you can find. You can find an x out there. If you go to the left here, if you go to -1, is there a point when x is -1? Yep, there is one right here. At -2, is there a point? It's off the graph here, but it's down here somewhere. So in this case, everywhere on x, you will have something on that line. So for the domain here, we're going to say all reals. Okay, all real numbers. Okay, so the domain, all numbers, everything works. Likewise, if you look at y, same thing applies. When y is 1, is there something here? Does y get used? You know, when it's 1, yes. When y is 2, does that get used? Yes. If we look through there, same thing. So the range here is also all reals. Is this a function? Vertical line test. Let's draw a vertical line. No matter where we draw that, it's only going to cross in one place. So yes, this is a function. Is it a one-to-one function? For each x, is there a unique y? If you go, when x is 1, there's only one y. When x is 2, yes, there's only one y. It seems like that's true. For each y, is there only one x? When y is 1, is there only one x? Yeah. When y is 2, there's only one point here. So it looks like it's both in this case. So it looks like it's both the one-to-one and on 2. And of course, it's a line, not a bunch of dots, and so it's continuous. All right, let's take a quick look at a few things here and just see what these look like. First one here, is this a function? Dotted or a vertical line test. Anywhere we draw that, it's going to only cross in one place. So yes, that's a function. What's the domain? Well, this was just pretty much like our last example where look at the x values. Think about left and right. Will this graph of the line that we've drawn here keep going all the way to the right and all the way to the left? Yes, it will. So the domain, again, all reals. And same thing up and down. Now when we think about the range, it's the y. So will this graph keep going up? Yes. Will it keep going down? Yes. So all reals. So again, everything will be in the domain and the range. Okay, now it's starting to get a little bit different. Look at this graph down here. Is it a function? Well, let's think of a vertical line test here. Draw a vertical line. Any place I draw a vertical line, will it only cross one time? Yep, once there, once there. So this is still a function. What about the domain? Will this, again, now domain, think left and right. Does this arrow keep going to the right? Yep, keeps going forever and ever. Does this arrow go to the left? Keeps going forever and ever. So just like before, it looks a little different, but the domain would be made up of all reals. The range, now it's a little different. Okay, so now think up and down here. So going up, will both of these arrows, one or both of the arrows, keep going up? Yes. So they'll keep going up forever, but will they both go down? Or will one of them go down? No. They stop at a certain point. This point right here is the point where they stop at. They don't go any further down. So what we have to do for the range is we say, well, where is that graph? It's all of the numbers of y that are at -4 or above. So we would say y has to be greater than or equal to -4. So that's our range there. What about this one? Is it a function? Okay, let's do a vertical line test. Draw a vertical line. It crosses in two places at the same time. This is not a function. What's its domain? Well, look at left and right. Where is the graph? The line is going to the right. It'll go forever, but it doesn't go any further to the left past 1. So here we have to say x is greater than or equal to 1 for the domain. The range, think up and down. Does the line go up? Yes. Keeps going up, keeps going down. So range is all reals. And then this last example here with the domain and range. Vertical line test, by now you probably figured this crosses in a whole bunch of places, so this is definitely not a function. What's the domain? Does it keep going right and keep going left? Yep, it's everything, so all reals. And range up and down, does it keep going up and keep going down on the arrows? Yes, it does, so also all reals. All right, last concept here, we're almost done. Function notation. In function notation, it's a little weird here, but this right here, f of x is how it's pronounced, f of x. It's really basically just a big Y. It's really just a big Y. Okay, that's all it is. So what this really means is it really means y equals x to the third minus 3. The only difference is that in writing it this way, it's telling you already that this is a function. So you know it's a function already. You don't have to figure it out. But if you look at this, f of x, and then we want to find f of negative 2. Well, what changed? When in place of x, there's a negative 2. That means what they're asking you for is they're saying find this when x is negative 2. So all you do is plug negative 2 in here. So we've got f of x, or f of negative 2 now, since we plugged it in, equals negative 2 to the third power minus 3. All we do is work that out. So what's negative 2 to the third power? Well, it really means negative 2 times negative 2 times negative 2. So this would equal negative 8 minus 3. And then when we do negative 8 minus 3, we get negative 11. So f of negative 2 equals negative 11. Notice this is not, f is not a variable. You do not get f by itself. You do not divide by negative 2 on both sides to get f by itself. F of 2 does not get split up. Altogether it's y. You cannot split up y. So this is just saying that when x is negative 2, f of negative 2, this whole thing, or y, is equal to negative 11. If it helps you think of it this way, basically this point, what this is saying right here is the same thing as saying the ordered pair of negative 2, 11. It means x is negative 2 and y is negative 11. That's basically what it means there. Okay? What happens if they give you something like this, f of 2t? Uh-oh. There's a variable in there. What am I going to do with that? Same thing. Just plug it in for x. Simplify it as much as you can. You may not get a number like we did a second ago, but you can simplify it. So here's what we're going to do. We're going to say f of 2t equals 2t to the third power minus 3. Let's work it out. Well, this whole 2t gets raised to the third power, so 2 to the third power is 8, and then t to the third power is t to the third, and then we have minus 3. Can I simplify that anymore? No, that's it, right? T to the third and 3 are not like terms, so that's as good as I can do. So my final answer here would be that f of 2t would equal 8t to the third minus 3. And then our last one, we've got, uh-oh, look at this, t minus 2. Oh, goodness. Okay, what did we do before? We just plugged it in, right? Let's just plug it in. So f of t minus 2 equals t minus 2 squared plus 5. Now, you might be thinking right now, okay, that's a horrible t, sorry about that. Oh, we could just take t squared and 2 squared and be done with it. What does it mean when you square something? What it means is you multiply it by itself 2 times. So whenever you have a binomial like this, like t minus 2, you have to write this out twice. So it's going to be t minus 2 times t minus 2. You have to do that. And then how do we multiply 2 binomials together? It starts with an f. FOIL. Okay? So we're going to multiply these together. T times t is t squared minus 2t inside minus 2t. 2 times 2 is 4. and then you have the plus 5. Then you just combine all your like terms here, so you've got t squared minus 4t plus 9. And so that's f of t minus 2. So that's what you end up with. But the key thing there is just plug it in with function notation. Just plug whatever's in the parentheses here in for x, and then work it out. And whatever you get is what you get. If you can simplify it, simplify it. If not, then that's all you got. All right, well, that's it for this session. We'll see you again in section 2.2. Have a good night.